Stripping down science. The Naked Scientist.
Hello, welcome to this week's Naked Scientist with me, Chris Smith, and also here this week is Kat Arney. Hello, Kat.
Hello.
Now, this week we're going to be finding out how a company are offering to store a copy of your immune system on ice until you need it. Also, how scientists have turned the rabies virus into a nanoscale Trojan horse to help them smuggle drugs into your brain. We'll also be finding out whether the firstborn is necessarily the brightest, top of the IQ pile. A mirror on the moon. Researchers have come up with a way to build a moon-based telescope 1,000 times more powerful than the Hubble telescope. More on that coming up shortly.
Also this week, it's Armageddon! What happens when the Earth is hit by a massive meteorite? And is that really what did for the dinosaurs? Or was it a massive volcanic eruption? We have Janet Sumner here from the Open University to explain all that, all the apocalypse. We'll also be shaking up the world of seismology to find out how earthquakes work with Columbia University's Peter Kellerman, and finding out how earthworms are helping scientists to clean up arsenic in Argentina. And in our kitchen science this week, we'll be finding out whether that old thing about tapping the top of the fizzy drinks can before you open it really does stop it spraying all down your top.
So if you want to have a go at that, grab a couple of cans of pop, and we'll be linking up with Ben and Dave. They're at Kegs in Essex, and we'll be joining them in a moment or two to find out how to do that experiment. Also, here's this week's teaser question. You can win yourself a copy of a fabulous new book. It's been published by Penguin, and it's called The Rough Guide to the Earth. So a lot of what we're going to be discussing this week is in that book. It's a fabulous new book, and I'll also throw in a signed copy of our book, which is Naked Science, and that comes also, added bonus here, it comes with a guarantee to brighten up the conversation even at the dullest dinner party. So if you want to win a copy, can you tell us who developed the scale that's used to measure the strength of an earthquake?
The Naked Scientist podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
A really interesting thing that's been announced this week is there's a company in the UK, and they're called Life Force, and they're offering, Kat, to take samples of your pristine immune system when you're in the throes of your youth and health and store it on ice so that should you ever succumb to some kind of disease later in your life, you could thaw out your frozen immune system, put it back into the body, and therefore reset your immune clock by 25 years or so, or however long you've had it stored for, because there are lots of people who have various diseases such as cancers and things. They then have to have chemotherapy which can blunt their immune system and make them vulnerable to infections because the immune system after that kind of treatment doesn't work so well. So they're saying we could put these banked cells, which they've stored in liquid nitrogen, and then they've expanded the numbers of those cells by adding various growth factors and things back into the body and reset your immune system.
Well, it sounds pretty interesting. And another aspect of this that they're proposing is that, for example, for treating cancer, you could thaw out these immune cells and then train them by mixing them with other cells or with molecules to recognise cancer. And it's something that's kind of at an experimental stage at the moment. It's quite interesting. But, it depends if you're a gambling man as to whether you think that it's going to be available as a treatment in a couple of decades' time.
Another thing they've suggested is things like HIV, which dismantles your immune system, and people obviously succumb later down the line to various infections because their immune system's been dismantled and can't effect a very good defence. They're saying you could put this back in to the patients whose immune system's been destroyed by something like HIV, and it would give the person a bit more sort of immune vigour, if you like. But I have a problem with that, which is that the reason people die with HIV is because the virus evolves in that person and eventually becomes a form of the virus that the immune system can't recognise, and that's why it can then attack you so efficiently, and it takes time for that to happen. So if you just put the immune system back in, it's still going to have that sort of loophole in it, so the virus should still be able to win.
Yeah. I mean, do you think you'd have it done? Would you freeze your immune cells?
Well, I don't see why not, because you are merely sort of freezing something which you've got plenty of anyway. We've got millions and millions of white blood cells in the body, and if you froze a sort of cross-section of what your immune system's doing at any time, there's no reason why your body wouldn't just accept them back later, because they're part of you.
Yeah. It's a question of money, though. I don't get paid.
It's not cheap. You do have to pay them, obviously, to bank the cells and then keep them on liquid nitrogen.
Because you can't just stick them in the back of the freezer with the frozen peas, unfortunately. Anyway, a study in the latest edition of The Lancet suggests that a new type of gene therapy might be a safe and effective way to stave off the symptoms of Parkinson's disease. Now, so far, it's a really small trial, and there's been about 12 patients with advanced Parkinson's. They've been treated over 3 years in a small-scale trial. And the treatment involves injecting a virus that's been genetically modified to carry the gene for a protein called GAD, and this stands for glutamic acid decarboxylase. Now, this protein's vital for producing a neurotransmitter in the brain called GABA, And this production is faulty in Parkinson's, so the brain kind of goes into hyperdrive and causes problems like tremors, stiffness and all these kind of things. So adding extra GAD through this virus is thought to boost the levels of GABA, and it helps to damp down this hyperactivity. And after treating these patients, they had on average about a 30% improvement in symptoms after they'd done things like brain scanning.
How did they get the virus in? Sorry, how did they actually get the virus to get into the brain to deliver the GAD?
It's an injection. I think this was an injection actually into the brain.
So it's quite traumatic.
So, yeah, it's but at the moment they've just done this small-scale trial. So the next step is to try and do a larger-scale trial, a sort of placebo-controlled trial to see how effective it is. And also it's worth stressing that the treatment's not going to get rid of the disease, but it should help to damp down the symptoms of it.
Well, I was just thinking, because this next item I read this week, which is in the journal Nature, has been done by a guy in Harvard in the States called Manju Swami and his crew. And they have managed to exploit the virus rabies, which everyone's acquainted with because it's one of nature's nastiest pathogens. And they've turned it into the equivalent of a Trojan horse. They've borrowed the coat of the virus, which is something called RVG, rabies virus glycoprotein. And because rabies invades the nervous system, this coat protein naturally has the ability to lock on to what's called the blood-brain barrier, which keeps the brain isolated in its own sort of cocoon in the body. And the virus knows how to penetrate that. So the researchers have been able to link this protein from the surface of the virus to various things, including molecules like drugs that you want to move into the brain. And then they injected it into mice, and it went round the bloodstream, locked onto the blood-brain barrier, and then carried the drug into the brains and into brain cells in these mice. And they were able to even use this technique to shut off genes, including the genes of infecting organisms and viruses. So you could cure these mice of a fatal brain infection using this technique. So I think that's amazing.
That's really exciting, because things like treatments for brain cancer and diseases like Alzheimer's and Parkinson's, they do have a real problem with getting into the brain because the brain's so good at keeping stuff out.
As you just said, you have to just drill holes in people's heads and put injections in. Well, if you could use this kind of technique, you might be able to bring in various factors that will boost the levels of this enzyme you mentioned, GAD, which boosts the GABA in the brain, and you could do it without having to drill holes in heads to do it.
Pretty exciting stuff. So there was a good side to rabies after all. Anyway, here's some news that confirms what I've thought for some time. And that is that the oldest child in a family, like me and like Dr. Chris, is likely to have a higher IQ than his or her siblings. Now, this was published
Even if you say so yourself.
Even if I say so myself. My sisters are, though, much more beautiful and attractive than I am. So, you know.
No comment there, Kat.
Upsides and downsides to this. Anyway, it's been published in Science this week, so it must be true. A Norwegian team has found that the firstborn children in a family, or those who'd actually lost their elder siblings and had therefore become the oldest, scored higher on intelligence than their pesky little younger brothers and sisters. And the team studied more than 250,000 men in Norway. And although the difference in IQ between siblings was quite small, it does work out as being statistically significant. And what's really interesting about this is that it's not the absolute order of birth, but your position in the family that's important. So some researchers have previously suggested that differences between siblings are due to different hormone levels and antibody levels in the womb with successive pregnancies. But this study shows that it's more likely to be social factors, so things like the amount of time that parents have to spend on firstborn children, and things like older brothers or sisters maybe kind of tutoring or looking after younger
older brothers and sisters can't be as good at tutors as parents then, because otherwise the younger siblings will be as intelligent as the older one, or better, wouldn't they? They're not.
Well, it's thought that actually teaching other people helps to boost your own
I think they teach
IQ.
them bad things, and I think they're a distraction. And I know this because my brother was very often distracted by what I was up to instead of doing what he should have been doing. But
those pesky younger brothers.
I've got a great thing here, which is to finish off with, which is I've called this Mirror Mirror on the Moon rather than Mirror Mirror on the Wall. But very excitingly, scientists reckon they can make a telescope that's 1,000 times more powerful than the Hubble Space Telescope. And you know how powerful that is. It gave us these wonderful pictures of way back in time, because you could see light that came from stars that no longer even exist, from the very early vestiges of our universe. And this is really natty, because what they're saying is you could make a moon-based telescope that would have a mirror in it made of a liquid. Now, sounds a bit weird, but why would you use a liquid? Well, the answer is if you choose the right liquid, when you spin a liquid under the force of gravity, and you can do this on Earth, and the moon's got gravity, so it will work there, the gravity pulls the spinning liquid into just the right shape to be the perfect mirror. And what these guys, under the sort of guidance of Roger Angel and his colleagues over at the University of Arizona, have done is to find a liquid, an ionic liquid, which can be still a liquid at the freezing cold temperatures on the surface of the moon. And they've managed to make this liquid, or made a right choice of liquid, so that when the pressure is zero, because there's no pressure on the moon either, it won't boil off, it won't evaporate. And then they've worked out how to spray it with silver particles, so you can make this liquid surface into the perfect mirror. And this, they reckon, will give you the ability to capture huge amounts of light, because this mirror could be huge, and this will give you glimpses way back in time, further than we've ever seen.
I think it will still make my bum look big, though. Anyway, you're listening to The Naked Scientists, and we're here. Coming up later, we're going to be talking about Armageddon, meteorites, volcanoes, earthquakes, explosions, all that kind of fun stuff. If you've got any questions about the Earth sciences, seismology, all that malarkey, or any general questions about science, medicine, technology, email chris@thenakedscientist.com.
The Naked Scientists, supported by the Wellcome Trust.
Now, since we've been talking about things we're going to be talking about things which have got inherent risk and hazards associated with them, we thought we would invite onto the programme someone called Joel Veitch. And Joel actually is from the website rathergood.com. And Joel, it's interesting because you wrote to New Scientist last year and said that you were a bit concerned about all these measures of things, how we quantify hazards and risks and things. Tell us a bit about that.
Well, yeah, I did notice that people were starting to talk about nanohazards and whether there should be warning signs for them, that sort of thing. And it struck me that really no one had really defined what a nanohazard actually is, because it turns out there is no SI unit for the measurement of hazard. So an SI unit is like a metre is an SI unit of length, for example.
So what are you proposing?
Well, I had to look into the statistics, because without statistics, science is nothing. And I thought, well, really what we should do is we should find something which poses a decent amount of hazard to a large number of people. So having looked through, I realised that curtains, which are something that, of course, most people are exposed to on an almost daily basis.
What sort of curtains did you have in mind, then?
Actually, it's non-specific. It's any kind of curtain. So if you have curtains in the home, then this is a hazard which applies to you, obviously. Looking at the statistics for 2002, they actually caused 4,080 injuries in 1 year.
So what, people closing them, opening them? This is the classic joke when someone goes to the doctor and says, doctor, I feel like a pair of curtains. The doctor says, pull yourself together. I mean, this is what I'd like to say to whoever did this survey.
It doesn't specify the kinds of injuries. One can only guess, but it does specify an awful lot of other things which can cause injuries, and I hate to imagine what those injuries might be.
Well, I had a look at the Royal Society for the Prevention of Accidents' website, in which they publish some of these details. And not surprisingly, building and DIY causes about 1 million accidents a year nationally. But then I had to look further down. I mean, looking at this, bread bins are absolutely lethal. 185 people a year are injuring themselves on bread bins. We need some kind of warning and regulation on bread bins.
It's true. We should. And interestingly, having another look through there, you'll see that some things which you would have thought would be inherently evil are in fact quite benign.
Well, compasses and dividers. I mean, a compass, nice big pointy spikes in it, the kind of thing teachers would love to ban from classrooms. 0 accidents last year. We need people injuring themselves with these things, so we get them banned.
That's right. And a mincer, 1 accident with a mincer, and again with a mangle.
Well, paper clips apparently caused 62 injuries last year, which is devastating. Maybe we should ban those.
Maybe we should. I've never found them terrifying myself, but,
But returning to the sort of curtain issue,
yes.
What did you propose that we should do in terms of coming up with some kind of nomenclature and unit of risk then?
Well, yeah, assuming that we actually need a unit for the measurement of hazardicity, or risk, as we could say, I would say that the risk posed by a curtain over 1 year, being substantial as we now know, should be the unit of measurement. So 1 curtain would be that amount of risk. And then we could measure the risk posed by other things in relation to their hazardicity compared to curtains.
So building and DIY would be like a mega curtain?
Yeah, or possibly even a giga curtain. Depending on...
So, do you remember when you used to go to the theatre and they'd have the smoking curtain?
Yes.
That's going to go out on the 1st of July, so I suppose that's a bit of a shame. But so vacuum cleaners, which cause 10,000 injuries every year, I perished the thought, why? If people didn't hoover naked, I suppose it wouldn't happen. But that would be, on your scale then, that would be roughly 2 times 4,000, that would be 2 curtains of risk.
Yeah, just over 2 curtains, yeah.
OK, so what's a really small risk then?
Well, one good example would be an artist's brush.
How harmful is that, then? Well,
in fact, that is how sensitive the data set is, and by that I mean the the data we've got only goes down to 1 accident per year in the UK, or in fact 21, because it's only 1 in 21 people covered by the survey. So there's only 60 million people in the country. So that means that you can't have, literally every possible hazard, because if there's no one injured by something in this country,
you can't quantify
then it doesn't, it doesn't figure on the stats. So we can go down to, for example, an airbed poses a risk of exactly 1 centicurtain, pretty much. So 1/100th as dangerous.
How do you injure yourself with an airbed? I mean,
well, I presume maybe some kind of bouncing, or I have actually gone a bit faint trying to inflate them myself from time to time, so I can see how that could result in a falling over.
Right, so what do you think the chances of Downing Street embracing your proposals and us having a warning system based on the curtain level of risk?
I think that really depends on how much of a fuss we kick up, really, doesn't it?
Are you going to take this to the House of Commons?
Well, we should. I mean, it occurs to me we have a new Premier coming in, don't we? So maybe we should give him the opportunity to
well, they're really quite...
This
government really quite into regulations and things, aren't they? I also noticed that on ROSPA's website that a real hotspot for accidents and damage are in cemeteries, which I think is quite appropriate, really, isn't it? You're in the right place to injure yourself, because then if it's really fatal, you can just fall into a hole and that's that. But
yeah, I suppose so, yeah.
Thank you very much, Joe. It's been great having you on the programme.
Oh, thank you.
Joel Veitch from the website rathergood.com, talking about how we need to have some kind of quantification of risk so that we can regulate things more appropriately.
Absolutely. And speaking of risks, we have our teaser today, which
that's not a risk, is it?
Well, no, there's no risks involved in answering our teaser unless you can stick your phone up your nose or something. But we want to know who developed the scale that's used to measure the strength of an earthquake. I reckon earthquakes are probably measured in terror curtains. We've had a few answers in so far. Alan in Bar Hill on the right lines, Tony in Westcliff, Linda in Royston, Pat in Sandon, Katie in, apparently, Curtin, Iris in Polchester and John in Warrington. You're all going in a hat because you've all got it right.
Now, have you ever wondered how dangerous, talking about risk, a can of fizzy drink can be? Well, we've got Dave and Ben standing ready and waiting at King Edward VI Grammar School, loaded with their fizzy drinks to test this urban myth. So, guys, what are you up to?
Hello, welcome to Kitchen Science. This week we're in King Edward VI Grammar School in Chelmsford, and I'm, of course, here with Dave Ansell.
Hi.
And I'm also here with Bryn.
Hi.
And with Henry.
Hello.
And Dave told me something about exploding pop cans today, but Dave, what's the plan? This sounds sticky.
OK, so what you need for this experiment is 2 cans of fizzy drink, ideally a diet one. And that's it, really.
So just 2 cans of fizzy pop?
Yeah, that's right. So what I want you to do is shake up those cans, put both cans in the sink. I want Bryn to tap his 4 times, quite hard on the top. And then we're going to wait about 5 seconds and open them both.
Now, you see, I used to do this at my school as well, but we always did it to play tricks on people. So what do you think is going to happen, seeing as we're shaking these cans up?
Well, if I do get wet, which I probably am, I'm not going to be very happy.
Fair enough. And what do you think?
It's going to explode everywhere.
OK, so Dave, you seem to be making kids explode cans all over themselves. Is that your plan?
Pretty much, yeah.
Okay. So what do you think will happen at home? Do you think that tapping the top of a can will make any difference? If you want to try this at home, I recommend you perhaps use a bathroom or a kitchen sink, but we'll get back to you later on in the show.
Thank you, guys. So give it a go. Grab 2 cans, shake one up, open one, tap the other on the top before opening it, open it up, tell us what happens.
Now, we've had some emails in this week, and a few weeks back we were talking about mobile phones being used in petrol stations, which is thought to be a hazard, and we were sort of having this discussion and thinking probably it's not that hazardous after all, because mobile phones don't very often cause any kind of sparks. But we've had Andy Munro in Western Australia who's emailed in, and he said he was wondering if there should be a sign at fuel stations about football shirts causing sparks, but especially these nice nylon-y football shirts that
don't judge everyone by your own standards.
If you take them off in the dark, they spark. So he's seen sparks from shirts, but never seen sparks caused by a mobile phone. So should we have, no football shirts at our petrol station?
I think he's got a really good point. I mean, this whole business about mobile phones, people say mobile phones emit microwaves, the microwaves get into metal things, they can induce a current, this might make a spark. But I've never seen one. It's theoretical, it's never been proven, yet you can have people jumping in and out of their cars wearing very slinky nylon underwear and making lots of static electricity on their car seat, or rubbing their shirt all over their head, that kind of thing. And that will make static and they will make sparks.
Yeah.
So we should ban people from going into garages
wearing
in
nylon
knickers, even, and including the men.
Yeah, no nylon knickers and football shirts.
Now, I've got a quick email here from Pete Sula, who is, I think, your biggest fan cat, because he said in the last 11 months I had 3 CAT scans, boom, and one PET scan, so he's obviously got a dog. The last two CAT scans said no contrast, which was apparently something you had to take 15 minutes before the scan. What is this contrast, and what does it bring out? And then he goes on to say, the next time I come to England, can I have a CAT scan there? Because then Dr. Cat could do it, and I could have a medical first, a CAT scan, and if Cat's got a cyst called patula, I could have a PET scan then. And he then goes on to say they thought he had lung cancer, but actually it was scar tissue in his lungs caused by the Korean War, where he was running around at minus 40 degrees Fahrenheit.
Oh, that's lucky.
I'm not entirely sure how that happened. The answer to that question is contrast is a substance you inject into people, which is usually things like barium or iodine. Hope you don't inject barium, it's not very nice, but iodine, it's big nuclei which scatter X-rays, and so they go around in the bloodstream, and if you have a cancer or something, the blood vessels supplying a cancer are leakier than the blood vessels supplying healthy tissue, so you tend to get a build-up of the contrast agent in the actual area that's abnormal. When the scanner comes along and zaps you with X-rays, the X-rays go right through normally, but where the contrast is, they get scattered and soaked up. So they don't get through, and so this makes the tumour, or whatever area of abnormality, glow up, if you like a hot spot. And so as a result, you can pinpoint areas of abnormality using this contrast agent. It makes areas of damage easier to see, basically.
We've got an email in here from Akshay Rao from New Delhi in India. So, hello, Akshay. Nice to know you're listening over there. He has a question about sleep, and he says he's often felt his leg muscles suddenly jerking a few minutes when he lies down to sleep. And it's usually preceded by a dream where you're about to fall. And I get this as well, when suddenly you sort of jerk and wake up. And
it's because you realise you're late for the Naked Scientist show.
Yeah, usually. Is that's caused by your brain and you slowing down
jerk.
to sleep,
yeah,
isn't it?
When you go to sleep at night, your brain paralyses your body, because what you don't want is for you acting out all your dreams, especially your dreams. But what would be it would be really rather devastating if you know when you're running away or fighting with people, if you started doing that in your sleep, because not only would it mean the person in the bed with you would have quite a rough night's sleep, but also it could be damaging to you. So your brain paralyses the body when you go to sleep to stop you being able to do that. And as that system kicks in, what happens is that you can sometimes have these hypnic jerks where all the muscles contract suddenly and violently, and you go, ooh, what was that? And for some reason it's associated with the dreams like falling off a cliff, that kind of stuff. But it's called a hypnic jerk. It's quite normal. Lots of people have them.
Fair enough.
Now, it is The Naked Scientist, and we have a teaser running this week, because in a second we're going to be talking all about the science of geology and mega eruptions and disasters and that kind of thing. But we also have our teaser, and we want to know who invented the scale which are used to measure the strength of earthquakes.
And now it's time to hop stateside to find out what Bob and Chelsea are up to in this week's Science Update.
Well, we know that the topic on Naked Scientist this week is natural disasters, but we haven't reported on any interesting natural disaster science for a couple of weeks. So now for something completely different. 2 stories on health. I'll talk about the depression-busting action of yoga, but first, Chelsea's here to answer that age-old philosophical question, what's the sound of one bicep flexing?
Doctors listen to your heart and lungs. Someday they could also listen to your muscles. Yes, your muscles make noise as they contract, and if you listen carefully right now, you can barely hear the sound of a bicep, sped up so it's audible. It was recorded by acoustician Kareem Sabra of the Scripps Institution of Oceanography, who placed sensors along the bicep. His team has shown it's possible to use this noise to detect a muscle stiffness.
And the main idea is that if the muscle is stiff, wave propagates fast into it. If the muscle is soft, wave propagates slower.
The technique needs more work, but it could prove useful for monitoring neuromuscular diseases or even diagnosing pulled tendons. And it could also cut down on the need for X-rays and MRIs.
Thanks, Chelsea. In other health and fitness news, scientists have found that yoga may boost brain chemicals that stave off anxiety and depression. This according to a study led by Chris Streeter, a psychiatrist and neurologist at the Boston University School of Medicine. The study focused on a chemical called GABA, which is known to be low in people with depression and anxiety. Streeter's team measured GABA levels in the brains of experienced yoga practitioners before and after an hour of yoga postures and breathing exercises. A control group simply read for an hour.
And the yoga people showed a 27% increase in GABA levels as a group, and the controls had really no change.
While this study can't prove that yoga alone would have this effect, some other studies also suggest that yoga may combat mood disorders, especially in combination with traditional psychiatric treatments.
Thanks, Bob. Next time we'll really tell you what happens when you mix a baby with a trumpet, because we didn't get to it this week. Until then, I'm Chelsea Wald.
And I'm Bob Hirschon for AAAS, the Science Society. Back to you, Naked Scientists.
Thanks, guys. And you can find out more from the Science Update team on their website, which is scienceupdate.com.
It's The Naked Scientists with Chris and Kat, and we're joined this week by, first up, Janet Sumner from the Open University. Hello, Janet.
Hi, Chris.
Thank you for coming in. Now, tell us, you're interested in looking at the subject of why we get mega eruptions and meteorites and things that wipe stuff out.
Yeah, I work on natural hazards, and they're pretty much larger things than Joel's curtain hazards. In fact, they're pretty big natural hazards.
This would be a sort of giga curtain.
It would be a super giga curtain, yeah. It's the kind of thing that really results in a global mass extinction. You know, that's a total eradication of entire groups of species. We're talking like the death of the dinosaurs here, basically.
So what do you think actually triggers the death of the dinosaurs? Do you know what it was? Was it a massive great eruption? We're all used to the idea that some kind of meteorite slammed into Earth. Which do you think it is?
Well, that's true, actually. I mean, it was, and it still is, widely believed that the dinosaurs were wiped out by the impact of the Chicxulub meteorite into the Yucatan Peninsula in Mexico about 65 million years ago. But there have been 5 great mass extinctions in the past 450 million years. And the dinosaur one is the only one associated with a meteorite impact. All the other mass extinctions, including the dinosaurs as well, all correspond to the outpourings of huge flood lava eruptions.
Well, if we could look at both of those things in turn then. So the meteorite that slammed into the Gulf of Mexico, how big would that have been to have been able to alter the planet so dramatically that nearly all life ceased?
Well, it was many, many tens of kilometres across. And basically the effects of a large meteorite impact like that are devastating. But the fact is, because we'd had this really long-running volcanic eruption going on for thousands of years, the dinosaurs were already on the way out, and all the impact did was finish them off a bit quicker.
Oh, that's interesting. I didn't realise that the dinosaurs were already waning, because I thought they were kind of at their peak around that time.
No, they'd already pretty much had it, because there'd been one of these huge flood lava eruptions going on in India for many thousands of years. And what we now know happens with these flood lava eruptions is, when a volcano explodes, it releases ash and sulphur. That gets up into the atmosphere, and it produces a kind of blanket in the atmosphere, and that prevents the sun's rays from getting through. So it causes a global environmental change. And interestingly, it's actually the opposite of what's going on at the moment, because right now we've got global warming. When you get a big flood lava eruption like this, you actually get global cooling, because this blanket stops the rays of the sun from getting through and keeping us warm.
So what actually is this flood lava? Where does it come from? What provokes it? And why is it so devastating?
These massive eruptions are often associated with plate tectonic movements and rifting and big upwellings of hot material coming out of the mantle, and they can break through cracks in the surface. And as I say, they can go on for thousands of years, and they can produce piles of lavas that are up to 3 kilometres thick. Now, the thing about the sulphur and the ashes, you've got to get it up into the atmosphere for it to do its work. And for a long time, scientists thought that flood lavas just kind of spew out onto the ground really quietly and then just flow off. The research that I've been doing has now proved that that's not the case, because I found lots and lots of beds of ash within these flood lava successions. And where you've got ash, you have to have an explosive eruption. So now it looks like that these flood lavas are coming out so violently that the molten rock is being ripped to bits and forming a huge curtain of fire, topped off by a massive ash plume. So, hey presto, now we can get our ash and sulphur up into the atmosphere and cause enough global cooling to cause mass extinctions.
So when was the one which had done for the dinosaurs? You mentioned briefly.
Chicxulub impact, that was 65 million years ago.
That was the meteorite?
That was the meteorite.
When was the big lava outpouring that had already begun to see off the dinosaurs then?
It started about just over 65 million years ago. So it was exactly the same period. It just precluded, or was just in front of, the Chicxulub impact, which happened virtually at the end of it.
And where was all that lava coming out? Was this a sort of unstable period of Earth's geology, so it was happening everywhere, or is it just one place on Earth?
They tend to happen periodically in different parts of the Earth. The one I was looking at was actually in India, as rifting was starting to happen in India. But we've also got one closer to home in the North Atlantic Igneous Province, just up to the north of us. They've also got one that have happened in Africa. So they happen all over the world at different periods.
So how could people have missed this before? Because I know everyone's attention's been focused on the idea that a meteorite arrived, it changed the Earth's weather so dramatically it wiped out the dinosaurs. How could they have missed 3 kilometres thick of lava deposits?
Well, we knew it was there, and we knew that large flood lava eruptions do cause mass extinctions because of this really strong correlation. What we didn't know the mechanism for getting this ash and sulphur up into the atmosphere to actually cause the global cooling, because everybody thought the lavas just flooded out, hence the name, flood lavas. But now we know that there is a mechanism for them to come out explosively and actually to put that ash up into the stratosphere where it can do its damage.
So is there any chance of one of these flood lava situations happening again? Are we due one?
That is always the question that everybody asks. Are there going to be any more mass extinctions? And why? Because we're worried about us, aren't we?
Yeah.
Well, the answer is yes, there could be another mass extinction. One, if we were hit by another really big meteorite. And two, if we did have another flood lava eruption. But what is more likely to happen, a much bigger hazard for us, is if we have a supervolcano go off. Now, supervolcano eruptions happen every 50,000 to every 100,000 years. And there are a number of supervolcanoes around the world. And one particular candidate is long overdue, and that's Yellowstone volcano in the US. Now, that is overdue by some thousands of years. So if that was to blow, it probably wouldn't cause global mass extinction, but it would certainly cause global famine. And that would probably mean the end of civilization as we know it.
What's the prospect that it will? What's going on there? Because people say the land is moving. And how long has it probably been there?
Oh gosh, Yellowstone has been around for hundreds of thousands of years, and I think it's had 3 major eruptions in its lifetime. It is due for another one, and scientists have seen that the land is doming up. But, I mean, it could be another 50,000 years before it happens. It's very, very hard to predict with these things.
Will it definitely go bang, or could it just sort of go fut like a failed firework?
I don't think it's going to go fut. I think the chances of a big bang are probably fairly high. But I don't want to be too depressing here, doom and gloom. But what I actually wanted to say was, have you ever seen a meteorite?
Actually, I have, but that was because I saw it in a museum. I've never actually held one.
Well, if you want to hold something from outer space, you can, because I've got one in my pocket.
I brought my mother-in-law to see me. Let's see. Oh, wow.
I want it.
Now, that's a Stony Iron meteorite.
This is incredible.
I want to see it.
This is. I'm holding a pebble, which is just sitting in the palm of my hand. I'm going to give it to Kat in a minute because she's itching to look at it. But it just looks like any other lump of rock, although it looks a bit iron. It's a bit rusty. Has it got some iron in it?
Yeah, it's a bit rusty on the outside, and you'll see it's got one polished cut surface on it, and you can actually see the iron glinting in there. So that's a lump of rock and iron, which makes it a Stony Iron meteorite. Now, if you notice, the outside of it is quite smooth as well.
Yeah.
That's actually something called a fusion crust, and that has happened as it actually heated up and started to melt as it came through our atmosphere and ultimately landed on Earth. Now, that one's only about as big as a golf ball, but it's also quite heavy because of all the iron in it. Now, if you can imagine a much, much larger scale meteorite and that hitting the Earth, it would probably make a bit of a mess.
That would be about 4.5 billion years old, presumably. The age of the solar system, presumably, that one.
Yes.
So that's pretty impressive. I don't think I've ever held anything quite that old.
This is pretty cool.
Well, it's nice to handle.
Doesn't make great radio, though. Ooh, look at this.
We'll put a picture of it on our website. This is The Naked Scientist with Chris and Kat. We've just been talking to the Open University's Janet Sumner. She's here with us if you'd like to ask her any questions about the kind of thing she's been talking about, supervolcanoes, massive outpourings of lava, or massive meteorites that slam into the Earth and wipe out life as we know it. Up next, Peter Kellerman's on the way. He's going to talk about the science of earthquakes. But if you fancy having a go at kitchen science, don't forget 2 tins of drink, shake them up, tap on the top of one, open both simultaneously, tell us what happens, or if you want to have a go at our teaser.
We want to know who was the inventor of the scale that we use to measure earthquakes.
Laying the facts bare, The Naked Scientists.
You're listening to The Naked Scientist with Dr. Chris and Dr. Kat, and we're talking about natural disasters, the really big stuff, volcanoes, earthquakes and all that malarkey. And we're joined by Peter Kellerman, who's from Columbia University. Hi, Peter.
Hi, Kat.
Hello, thanks for coming all the way over from the States.
Oh, yeah, just for this.
Just for this, it's great. So, tell us a bit about earthquakes. What's happening when an earthquake's happening?
Well, in general, what happens is that there's already a fault surface and there's friction on the fault surface. And as that's overcome, it becomes much easier for the rocks to slide by one another. So that's really crucial, that it's hard to get it started. And then once it gets started, it runs away.
And are all earthquakes the same? I mean, you sort of hear an earthquake has happened. Is everything the same? Are they the same speed? Where do they happen in the Earth?
Well, there's a huge variety of earthquakes, and maybe I'll just take the where question first, and that is, there's The big earthquakes are where the tectonic plates are sliding by one another, one way or another. And so the very biggest ones are in the subduction zones where oceanic plates are being slid beneath the continents.
So where do we have these around the world?
Well, they're in the Ring of Fire, so-called, or the seismic zone next to the Ring of Fire around the Pacific, and then in the Lesser Antilles and elsewhere.
So these are places like Japan that are particularly susceptible.
And then, of course, that kind of plate boundary turns into what we call a strike-slip fault, where plates are sliding by one another, and that's the big deal in San Francisco.
So the sort of earthquakes you're looking at, they're a particular type, aren't they, called intermediate depth? What does that mean?
Well, we were interested in those. I mean, first of all, I have to tell you, I'm not a seismologist. I'm a geologist. I just work on rocks. But we got interested in intermediate depth earthquakes because of things we saw in the rocks. And intermediate depth earthquakes have been hard for seismologists to understand because they occur beneath a big pile of rock that could be 50 or 100 kilometers thick. And so the ordinary kind of sliding on a fault surface is very difficult when you've got 100 kilometers of rock sitting on top of you. And so we see these shear zones that formed at those depths in the mantle of the Earth that are now exposed by plate tectonics. And you can see that there was no fracture, but there was a zone of very, very highly localized deformation. And sometimes you can see that these rocks got so hot that they melted.
And are these types of earthquakes particularly damaging?
Yeah, they're just as bad as the shallower kind. There've been some really big ones in Bolivia that were quite damaging to cities.
And we've got a caller now who wants to talk about earthquakes. Is that Mark?
Hello there.
Hello. What's
Hi,
your question?
My question is, when the geologists and seismologists talk about earthquakes, they very rarely mention the influence of tides. Many of the earthquakes, including the Boxing Day earthquake that caused the tsunami in the Indian Ocean a couple of years back, happen at a time of very high tides. And I just wonder what your geologist had to say about that.
Well, there is a well-known cyclicity with tides for micro-earthquakes, and presumably that extends to macro-earthquakes. There's this idea of sort of self-organized criticality, that things get poised on the brink of failure, and then just some very, very small phenomenon is all it takes to push them over the edge. And I wouldn't be at all surprised if there was a correlation in general between great earthquakes and tides.
Yes, I think you'll find if you look at many larger earthquakes and volcanic eruptions, if you just check the tide patterns, you'll find that they often happen at periods of higher than average tides.
Right, but that doesn't mean that if you live in San Francisco, you should worry every time the tide is higher than average.
No, but you could be aware at that particular time rather than other times.
Yeah, sure.
Yeah.
I suppose that the point that Mark's making to us, Peter, is that the moon is exerting a gravitational effect on the Earth, and hence, I suppose, if you've got water, big bodies of water moving, that's quite a big weight pushing down, isn't it? And I suppose that could make a difference to the way in which plates and tectonic interaction zones actually do interact, and therefore might actually suddenly release all the pent-up energy.
Without a doubt, there is a correlation, and you can watch now that we have instruments on the seafloor regularly, you can watch the mid-ocean ridges kind of breathe with the tide. The earthquakes and the hydrothermal water coming out, the hot water coming out, goes with the tidal cycles.
Thanks for that, Mark. It's a good question.
Yep,
really interesting. Good having you on the programme. Thank you.
Bye.
It's interesting because I, for one, was quite shocked. I looked at the US Geological Survey's website today to see, because they monitor earthquakes that are going on all around the world all the time, and I didn't realise that yesterday there were 22 earthquakes. Today, at lunchtime, there had already been 12 earthquakes, one of them in the middle of the Pacific, measuring almost 6 on the certain scale that we've been talking about this evening as part of our teaser. And I was quite surprised, actually, at how many there were and how strong they were.
Well, actually, it's kind of a matter of definition, and as our instruments get better, there are going to be more and more earthquakes that people are reporting. So the magnitude 1 and magnitude less than 1 earthquakes are extremely frequent and happen for all sorts of reasons, having to do, for example, people pumping water out of the ground.
And how is our knowledge about the sort of causes of earthquakes, some of the work that you've been doing, is it helping us to predict where earthquakes are going to happen any better?
Well, one of the most important outcomes of our research is the idea that even below the so-called brittle ductile transition, where it's very difficult for rocks to fracture, there can be non-steady deformation in the Earth. And because the mantle is much, much stronger than the crust, if the mantle is moving in a non-steady way, sort of jerking forward and then standing still for centuries, that's going to be extremely influential in terms of causing shallower crustal earthquakes. So if it is a factor, and we're not sure yet, it's something you'd have to know in order to predict the shallower earthquakes.
Thank you very much. That's Peter Kellerman, who is from Columbia University. He's in Cambridge for a conference at the moment, and he kindly agreed to drop in and tell us about his work on earthquakes.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Now, continuing our theme here on The Naked Scientists with Dr. Chris and Dr. Kat of hazards and that kind of thing, Michael Watts is with the British Geological Survey, and something you've been doing quite a lot of, Michael, is looking at Argentinian arsenic. Tell us about that.
This is a project that we're doing in collaboration with the University of Surrey. Professor Neil Ward actually set up this work. We're doing this through a co-sponsorship of a PhD student, and the idea is that she's looking at a northern region in Argentina, San Juan and La Rioja, well known for the wine. It's also well known for high arsenic levels in the local water systems and in the soils. So what we're doing is helping out local geoscience institutes and local universities, and with local medics, we're trying to build up a picture of what is actually going on. So we're sort of building up information in sort of three layers, working out the environmental geochemistry, so sort of surveying waters and soils for the arsenic content.
Where is all this arsenic actually coming from in the first place?
Well, the arsenic will generally be naturally occurring in the environment, but it may well be present in water systems due to mining activities.
The Victorians were very fond of it because it made very nice green wallpaper, and then made people go green and die. But you know, why actually is it toxic, and why is it something we need to worry about?
Well, it's a natural, it's a well-known poison. One of the issues is actually the chemistry of the arsenic and the form that it's present in. So that's something that needs to be considered. You may have a lot of arsenic present in the environment, but the toxicity and the availability to be taken up by humans is really dependent on the chemical form. So that could be the redox conditions, or the formation or the presence as an organic compound.
So when people drink water or eat food or whatever that's been grown on arsenic-contaminated land, that's the way in which they can get the arsenic into their body?
Yeah, or via hand-to-mouth contact. So if you've got a bit of soil on your hands, you've done a bit of gardening and you just touch your mouth, that's one way. Or soil attached to vegetables.
So how are you actually trying to study how much arsenic the people are being exposed to? Is there a way of doing that?
Well, with this Argentinian work, we're sort of building up a survey of, as I said, of the waters and soils, looking at agricultural products, and then that will lead to human studies. So with the help of local medical experts, we're collating information from rural communities and getting a sort of medical history of the people, where there have been a number of cases of deaths or even health conditions related to arsenic poisoning. But we really need to sort of confirm this anecdotal link between the environmental data and the end point where people are ending up with diseases.
Now, someone was saying to me the other day that earthworms are proving really quite useful in trying to work out what's in the soil. That's some work we've been doing in the UK. It's been well documented that earthworms are excellent indicators of the health of soil, and one of those uses is to look at the arsenic uptake in the earthworm and look at the effect on its health. We can do that by looking at cell damage as a result of exposure to arsenic. So rather than a canary in a cage, you've got an earthworm in the ground, and you can use that as the index of the degree of contamination. Yes,
there's a tentative link to humans there. It's more an indicator of ecotoxicity. We do use another technique called the PBET, which is a physiologically based extraction technique. And this is quite a popular technique for simulating the human gut. So what we do a laboratory-controlled experiment, and in a tube we'll put the soil into a tube and then add bile juices and acids and so on to simulate the stomach.
So it's like a sort of stomach in a dish?
Yeah, that's it really. And so we'll look at how much arsenic is released from the soil, so how much is available for the human to be taken up, how much arsenic is available to the human to be taken up. So rather than just looking at the total arsenic in the soil, we're looking at the accessible arsenic, which is a very important point.
And very briefly, Michael, if you discover there's lots of arsenic in the soil, what can you actually do to remedy the situation?
Well, that's quite a difficult issue. I mean, one of the most expensive remedies is to actually remediate the land and take it away from landfill and replace it. It's a very difficult thing to do, or seal the land. For communities in Argentina, that's a very difficult issue because basically reliant on subsistence farming. There might be a recommendation for filtering the irrigation water, whether there are engineering means to correct that, or maybe they source the water in other ways.
So really avoidance rather than cure at this stage, I suppose.
Yeah, I mean, it's a very difficult thing. That's beyond our expertise, really. I mean, we can build up the weight of evidence to suggest that the arsenic is there, and it could be a problem, or maybe it's just perfectly happy sitting there and not causing any problems. But it's really building up the weight of evidence so that sort of government institutions can come in and recommend methods of remediation.
OK. Michael Watts, thank you very, very much for joining us on the programme. That's Michael Watts from the British Geological Survey, who's been studying arsenic contamination in the ground over in Argentina.
And now it's time for our question of the week. And in last week's show, we tried to answer your question about the attractive forces of light bulbs on insects. And in response to that question, we've had an email from Bruno in Brazil. And he reckons that insects have a faster frame rate than humans. This means that they can see things faster than we can. So the light from a light bulb that may appear continuous to us, it might appear to be blinking to an insect. So it's this blinking effect that's attracting the insects rather than the light per se. And, you know, it's probably an interesting area for researchers to investigate. But Bruno suggests we probably need to be able to see like insects to understand the problem. But anyway, this week we have a question of the week, and we've asked, why do people get stuck in quicksand?
Hello, welcome to Question of the Week. Here with this week's question is Danny.
Hi, I'm Danny in Alaska, and I'd like to know about quicksand. Why do people get stuck in quicksand, and how can they get back out? Thank you.
Quicksand. Well, I'm stuck on that one. The expert with the answer is Daniel Bon from the Laboratoire de Physique Statistique in Paris.
So there's basically three myths surrounding quicksand. The first myth is that you shouldn't move when you fall into it. The second is that once you're stuck in it, it's impossible to get out. And the third myth is that you will eventually drown in it. Now, the first myth and the second myth actually turned out to be true. And we studied that using a natural sample of quicksand from Iran. Basically, if you move in quicksand, it becomes extremely liquid, and so if you really move violently, you will sink in at a great speed. So you indeed shouldn't move. Then once you're in, the sand grains in the quicksand will pile up around your feet, and that makes it incredibly difficult to get out of the quicksand again. Basically, we calculated the force you need to lift your foot at 1 centimeter a second is equivalent to the force of lifting a medium-sized car. But the third myth, that you can drown in it, which is a myth that is seen in many, many Hollywood movies, such as, for instance, Hound of the Baskervilles, is absolutely not true, and that's simply due to the buoyancy force. So we've known that since the old Greeks, since Archimedes. Basically, you're half as dense as quicksand, and so you will actually float in it.
Okay, so based on Daniel's expertise, here's the Naked Scientist's Quicksand Survival Guide. Number 1. Don't panic. Any violent movements will make you sink in deeper. The other reason not to panic is that actually you won't drown. Number 2, to get out, make small, slow, circular movements which should help to liquefy the quicksand, making it easier to escape. Phew. Here's next week's puzzle.
Hi, I'm Sebastian from London. I'd like to know what would happen if I was to fall out of a spacecraft without a spacesuit on. Would I explode as space is a vacuum?
Do you think you know what would happen to a naked astronaut? I'd like to hear all about it. Or perhaps you have a question of your own. Drop me a line to questionoftheweek@thenakedscientist.com. That's all for this week. Now back to the studio.
And that's Sabina, one of our naked scientists. And we've also had an email in about this from Philip in Los Angeles. And he says, if your leg gets trapped in quicksand, the grains of sand form a sort of a cone with your leg in the centre. And this is almost the same as our kitchen science a couple of weeks ago, where you had rice in a cup and you're sort of jiggling a knife around in it. And this is how you can sink in quicksand, but it's extremely hard to pull out of it. So to get out, you need to, as we said, wiggle your leg in a circle to get a layer of water going in between your leg and the sand. So you can get out that way. And if you think what would happen to you if you leapt out of a spacecraft naked without a spacesuit on, then do email us at questionoftheweek@thenakedscientist.com.
And if you've got any interesting and intriguing science questions that you'd like Sabina to solve for you, same email address. Now, in a second or two, we're going to be going back to King Edward VI Grammar School for our kitchen science. We asked you to pop the cap on a can of fizzy drink that you'd shaken up earlier and see if it sprays everywhere, and then take a second can and tap the top, having shaken it, and see if it doesn't spray everywhere. What did you find? Well, before we head to them, I've got some interesting emails come in. One's from Mark. He says, you guys keep me sane on the London Underground during the rush hour. I listen to your podcast. Can you explain to me why is carbon dioxide used to make fizzy drinks? Why not something else, some other gas, or plain air even?
Well, there's two reasons. The reason that you don't use oxygen for this is because oxygen is very good at oxidising things and makes them go off, so it probably wouldn't make your drink taste very nice. The other reason that we use carbon dioxide is that it's basically a neutral chemical. It doesn't react with stuff. So you can stick carbon dioxide in it and your drink's not going to go off. And also, carbon dioxide is based on an acid. So acids have a nice kind of lemony, sparkly taste in your mouth, and it makes your fizzy drink taste better. And along the same lines as fizzy drinks, we also have a question in from Jake Jennings, who's in Owensboro in Kentucky, which I'm assuming is in America. And he says, why is it when your beer's gone flat, the fizz seems to come back when you sprinkle some salt in the glass? Is there a chemical reaction at work? Chris?
No, what's actually happening is that when you've shaken up your drink and all the fizz has appeared to come out because it goes tss, like that, there's still a lot of carbon dioxide, the fizz chemical, dissolved in the liquid. So when you leave it standing for a while again, more carbon dioxide comes out of the liquid where it's dissolved and forms above the liquid again, so that it seems to have come back when you take the cap off. Or if you sprinkle the salt or the sugary things in, then you've got what's called lots of nucleation sites, spiky sites, where the gas finds it easy to form and you get fizz back again. Anyway, we're just about to rejoin Dave and Ben, who are over at Kegs, but before then, let's hear from Simon, who has had a go at the experiment. Hi, Simon.
Hello.
What did you find?
It actually did work.
Well, what do you mean?
It doesn't make you wet if you tap it 4 times.
Okie dokie, well, let's head back and find out if you're right. Stay on the line. Guys, what's the answer?
Welcome back to Kitchen Science. Now, for this experiment, you need 2 cans of fizzy pop, and we're going to shake them up as much as possible. We've got our 2 lads from Kegs School here, and they're still shaking their cans up, so they should be really well shook up now. Give them one last final big shake, and now, both at the same time, I want you to put them in the sink. And Dave, I'll let you lead them through what's next.
So you probably want to point them away from you at this point. OK, so now, Bryn, I'd like you to hit the top of that can quite hard, about 4 times. OK, so now I want you to open your cans. Henry first.
Fuzz everywhere, loads of liquid coming out, and it's all going down the sinkhole.
So we've wasted quite a lot of pop with that one spilling everywhere. Let's see what happens to the one that got tapped.
Well, actually, nothing came out. It was just a tiny bit of fizz, and it didn't even come next to the rim, so I think it works.
So, Dave, clearly tapping the top of a can saves you from a bit of a sticky mess and from wasting some of your drink, but why would that happen?
OK, if you come over here, I've got a couple of clear bottles of lemonade so you can see what's going on. So, Bryn, if you'd like to shake this up, and if you look at the side of the lemonade bottle, what can you see, Bryn?
The bubbles are just sticking to the side.
Yeah, that's right. So when we shook it up, we made lots and lots of bubbles, and quite a lot of them are still stuck to the side of the bottle. Now, Henry, I want you to open that bottle, and while you do it, watch the bubbles very carefully.
The bubbles are all coming up, and they're getting hot up.
It's not been our day today, has it? Mainly your day. It's been your day for soaking children.
OK, so it's really hard to actually start forming a bubble in a bottle of lemonade. But once one's there, it's very easy for it to grow. So if you've got a load of bubbles already started from when you're shaking it up, sticking to the sides of the wall, when you open it and release the pressure, it's really easy for those to grow. So they can get much bigger really quickly and make the amount of liquid in that bottle get hugely bigger until it spurts out everywhere. Now, what we're going to try with the second bottle is we're going to do the same thing, but just try tapping it on the floor a few times and see if it makes any difference. So, Henry, do you want to shake it? That looks good. So now what I want you to do is pick it up and hit it on the table a few times. Okay. Just gently.
bubbles are rising up to the top when they're unsticking from the side.
So all the bubbles are coming unstuck from the side of the bottle, and they're rising up to the top where there's a patch of air at the top.
Yeah, that's the idea. So if we just keep hitting it on the ground until we dislodge most of those bubbles.
Can you see any bubbles on the side now?
No, none.
So now, Henry, if you'd like to open that gently.
Some bubbles rose to the top, then it didn't go anywhere near the top of the bottle.
So you didn't get squirted on?
Nope.
So Dave, how come we shake one bottle up and we open it and everybody gets covered in lemonade, and then we shake the next one up but we hit it for a while and just the gas comes out but no water? Why was that?
Well, because all of the bubbles have managed to come up to the surface. If the gas at the surface expands, it will just hiss out. But because there's no bubbles inside to expand and blow the lemonade out the top, you stay dry and everything's fine.
So because all the gas that's under pressure is now in the top by the opening, and there are no bubbles under pressure down under the liquid, it means that when you open it, the pressure's released, the gas expands, but instead of pushing the liquid out of the way to get out, it just all comes out itself.
Yes, there's still lots of carbon dioxide dissolved in the liquid, but there's nowhere for it to form bubbles, so it doesn't expand.
So it stays as dissolved carbon dioxide instead of coming out as a gas?
Yeah, that's right.
So what do you think of that then?
Well, that was quite fun, getting some lemonade into my system. Yeah, the sticky part wasn't as fun as the other parts, but still, it was nice.
So will you be tapping all of your cans of pop from now on to make sure they don't squirt out everywhere?
Definitely. I don't want any more fizz over me.
Well, I hope nobody at home is quite as sticky with lemonade as we are here, but that is all we've got time for from Kitchen Science today. So, from Dave Ansell...
Goodbye.
From myself and from our wonderful helpers, Henry and Bryn, it's...
Goodbye.
That was so cool, because you often hear that trotted out, but you never know whether or not it's really true, whether you should believe it. So also well done, Simon, who tested it. He was calling from Braintree, said it was true, and he was absolutely right. So thank you to Henry and Bryn, who got wet in the name of science at King Edward VI Grammar School in Chelmsford.
It's good to know, because I always do that, and it's nice to know. I feel vindicated now. Anyway, we've had our teaser running all day, and we want to know who developed the magnitude scale that earthquakes are measured by. And our winner is from Bielefeld in Germany, and it's Christian Mertes, and he says it was invented by Charles Francis Richter and Benno Gutenberg, and they developed the Richter scale in 1935.
Oh, it's not called the Richter whatever then?
Well, it used to be called Gutenberg, but apparently it used to be called the ML scale. So Richter is relatively
He sort of usurped the true crown.
Yeah, he got in there.
Well, that's it for this week. Thank you very much for listening. Next time, it's our science Q&A extravaganza. The entire hour of The Naked Scientists will be devoted to answering your science questions, and the wackier they are, the better. So please send them to me now, chris@nakedscientist.com. And do also drop us a line, even if you haven't got a question, just to say hi, because we love hearing from you, especially if you're in some remote and very exquisite or tropical part of the world. And do also consider dropping by the Naked Scientist Forum. That's nakedscientist.com/forum, which is a thriving hive of scientific discourse. Go and check it out. It'd be great to see you. Have a great week. Thank you very much for listening. And thank you to our production team, Azzy, Ben, Dave, Sabina and Charlotte. See you next time.